A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. Imagine if your AI could write the next paragraph in the time it currently takes to write the next single word. That is the dream of real-time interaction, but as of April 26, inference latency is still the biggest wall we hit when deploying these massive models. Today's prompt from Daniel is about speculative decoding, which is essentially the clever hack that makes that dream a reality. He wrote to us saying that speculative decoding is the inference trick making large language models feel snappy. The core idea is a small draft model proposes several tokens ahead, then the big model verifies them in a single forward pass, and you accept the run of correct guesses. This gives a 2 to 3 times speed up with zero quality loss. He mentions variants like vanilla speculative decoding, Medusa, EAGL, and look-ahead decoding, noting that this works on any autoregressive decoder like transformers or Mamba.
Herman Poppleberry here, and I am legitimately thrilled Daniel brought this up. It is the most elegant cheat code in computer science right now because it exploits a fundamental hardware reality. GPUs are incredibly fast at math, but relatively slow at moving data from memory. By the way, today's episode is powered by Google Gemini 3 Flash, which is fitting because we are talking about the bleeding edge of how these models actually reach our screens.
It is funny you call it a cheat code. Usually, in engineering, when you want something to go 3 times faster, you have to sacrifice accuracy or use a smaller, dumber model. But Daniel mentioned zero quality loss. How do you get a massive speed boost for free without the model becoming less coherent?
That is the magic of the draft and verify framework. Think of the draft model as a fast-talking gambler making a string of bets about what the next words will be. If the big model, the judge, agrees with those bets, it validates them all in one go. If the judge disagrees at any point, the gambler has to stop and the judge provides the correct token. Because the big model always has the final veto power, the output is mathematically identical to if the big model had written every single word itself.
Okay, so let's break down the mechanics because this sounds like a bit of a paradox. You are telling me that running 2 models, a small one and a large one, is somehow faster than just running the large one alone.
It sounds counterintuitive, right? But it comes down to memory bandwidth. When you run a 70 billion parameter model to generate one token, the GPU has to load all those billions of weights from its memory into its processing cores. That loading process is the bottleneck. The actual math the GPU does once the weights are loaded is almost instantaneous. Speculative decoding says, while we have those weights loaded to verify one token, why don't we verify 5 or 6 at the same time? The math cost of checking 6 tokens is barely higher than checking 1, but the memory cost of loading the model is exactly the same.
So the small model acts as a scout. It runs ahead because it is tiny and light, so it can generate those 5 tokens super fast. Then the big model looks at the scout's work and says, yes, 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 no, that 4th word is wrong.
That is a great way to put it. And here's the kicker. If the big model accepts all 5 tokens from the scout, it actually gives you a 6th token for free. During the verification pass, the big model calculates the probabilities for the next step anyway. So if the draft was perfect, you get 5 plus 1. You just jump 6 words ahead in the time it usually takes to move one.
I want to dig into the math of that verification step for a second. If I am the big model, and I am looking at a sequence of tokens from a draft model, how do I decide to accept them? Is it just a binary? Is this the word I would have picked? Or is there more nuance to the probability distribution?
It is deep nuance. In vanilla speculative decoding, we use an acceptance criterion that ensures the final output follows the exact same probability distribution as the target model. If the draft model suggests a token that the target model also thinks is very likely, we accept it. If the target model thinks the draft's choice was a low probability fluke, it rejects it and resamples from its own distribution. There is actually a specific algorithm involving the ratio of the two models' probabilities. It ensures that the speculative part of the name does not mean guessing at random. It is a statistically rigorous verification.
So what does the scout or the draft model look like in practice? Does it have to be a specific type of model?
In the early days, like the original Leviathan paper from 23, people just used a smaller version of the same architecture. For example, if you are running Llama 70 billion, you might use a tiny 700 million parameter draft model. It has been trained on similar data, so it has a vibe for how the big model thinks. But as Daniel noted, we have moved way beyond that.
Right, he mentioned Medusa and EAGL. I am guessing these are not just smaller models, but different ways of doing the scouting.
Medusa is a fascinating one. Instead of having a second separate model, Medusa adds multiple heads to the very last layer of the big model itself. Imagine the model has one mouth usually, but you give it 5 extra tongues. The first head predicts the next token, the second head predicts the token after that, and so on. They all work in parallel. It is elegant because you don't have to manage a second KV cache for a second model.
But wait, if those Medusa heads are all part of the big model, aren't they just as slow to run?
No, because they are just single-layer feed-forward networks sitting on top of the final hidden state. They are incredibly cheap computationally. You are basically asking the big model's internal representations, hey, based on what you know right now, what are the next 5 likely steps? And these tiny heads give you a quick answer.
That makes sense. But then Daniel mentioned EAGO, which he says is the current state of the art for self-speculation. How does that differ from the Medusa tongues?
EAGL is brilliant because it realizes that words are not just words, they are vectors in a hidden space. Instead of trying to predict the next word directly, EAGL predicts the next hidden state of the model. It uses a very lightweight transformer plugin. Recent benchmarks have shown EAGL2 or EAGL3 hitting 6.5 times speedups. It is much better at handling the uncertainty of the draft because it works at the feature level rather than just the token level.
I am looking at some of these case studies Daniel sent over. There is one where a 7 billion parameter draft model paired with a 70 billion target model achieved a 2.5 times speedup on code generation. Why is code generation specifically highlighted there? Does speculative decoding work better on code than, say, poetry?
You hit on a massive point. Speculative decoding's efficiency depends entirely on the acceptance rate. If the scout is good at guessing what the judge will say, the system flies. Code is very structured and predictable. There are only so many ways to finish a for loop in Python, so the scout model has a very high success rate. Creative writing or complex logic is harder to guess, so the scout gets vetoed more often. When the scout gets vetoed, you lose some of that speed up because you spent time on a guess that didn't pay off.
That brings up a trade-off I was wondering about. Is there a scenario where speculative decoding is actually slower than just running the big model? Like, if the scout is a total idiot and get every guess wrong, are you just adding overhead?
Theoretically, yes. There is a small cost to running the draft model and a small cost to the verification math. If your acceptance rate drops to near zero, you are technically slower. But in practice, even a very small model is surprisingly good at predicting the and is of a sentence. Most implementations use a dynamic k-value, that is the number of tokens to guess. If the model sees it is getting rejected a lot, it might only guess 2 tokens. If it is on a roll, it might guess 10.
It is like a gambler who starts betting smaller when they are on a losing streak. I love that. Now, Daniel mentioned Mamba. We have talked about state space models before, but why are they ideal drafters for transformer targets?
This is really cool research from 25. Transformers have a KV cache problem. As the conversation gets longer, the memory the model needs to store grows and grows. If your scout is a transformer, it also has to manage a growing memory cache, which can actually eat up 20 gigabytes of VRAM in long context windows. Mamba models have a constant memory state. They don't care if the conversation is 10 words or 10,000 words. Their memory footprint stays the same. So using a Mamba scout to help a transformer judge means you get the speed without the memory bloat at long sequences.
That is such a smart architectural marriage. You use the efficient memory of Mamba for the scout, and the massive reasoning power of the transformer for the judge. It feels like we are moving toward these hybrid inference stacks, where it is not just one model in a box, but a whole ecosystem of components working together.
It really is an ecosystem, and we haven't even touched on look-ahead decoding. This one is for the purists who don't want a second model at all. It uses something called Jacobi iteration. Essentially, it treats the decoding process like a system of nonlinear equations and tries to solve for multiple tokens simultaneously. It is model-less speculation. It is not always as fast as EA-GEAL, but it is incredibly robust because you don't have to train a scout.
So if I am a developer listening to this, and I have a model that feels a bit sluggish in my app, is speculative decoding something I can just turn on? Or do I need to go back to school for a PhD in linear algebra?
The good news is that the major inference engines, things like VLLM, TensorRT LLM, and even smaller setups now have speculative as a flag you can toggle. You just need to point it to a compatible draft model. The industry has converged on this so quickly because the return on investment is massive. You are essentially getting a 3 times throughput increase on the same hardware. For a company paying for GPU cloud time, that is a 70% discount on their inference bill.
That is the real-world impact. It is not just about making the chat bubble pop up faster, it is about the economics of AI. If you can serve 3 times as many users on the same H100, your business model suddenly looks a lot healthier.
And it enables things that were previously impossible. Think about real-time voice translation or thinking out loud agents. If the model is too slow, the human element of the conversation breaks. Speculative decoding pushes the latency below the threshold of human perception. It makes the AI feel like a partner rather than a slow-loading web page.
I want to go back to something Daniel mentioned, the drafting tree. He said modern systems don't just guess a linear path, they create a tree of possibilities. How does the big model verify a tree? Does it have to look at every branch one by one?
That is the beauty of tree attention. It is a specialized attention mask that allows the big model to look at all branches of the tree in a single forward pass. Imagine the scout says, the next word could be apple, banana, or cherries. Then for each of those, it guesses 2 more words. You have a little branching structure. The big model looks at this whole cloud of tokens and picks the single most valid path through the tree. It is much more efficient than linear guessing because even if the scout's first guess is wrong, one of its alternative branches might be right.
That is like playing multiple hands of blackjack at once and only having to pay for the one that wins.
And there is even logic now using multi-armed bandits, a type of reinforcement learning, to decide which branches to prune or grow in real time. If the model is writing a technical manual, it grows a deep, narrow tree. If it is writing a screenplay, it grows a wide, shallow tree to capture different creative directions. It is becoming incredibly sophisticated.
What I find wild is that this technique is architecture agnostic. Daniel pointed out it works on transformers, Mamba, RWKV, basically anything that predicts tokens one by one. Does that mean speculative decoding is a permanent fixture in the AI stack? Or will we eventually just train models that are fast by default?
I think it is a permanent fixture. As long as we have the disparity between memory speed and compute speed, we will want to use this trick. Even if we invent a flash transformer that is 10 times faster, we will still want to run speculative decoding on top of it to make it 30 times faster. It is just too good of a deal to pass up. The only way it goes away is if we move away from autoregressive generation entirely, meaning we generate the whole sentence at once like an image. But so far, word-by-word prediction is still the king of reasoning.
It is amazing how much of AI progress is actually just very clever engineering around hardware limitations. We talk about intelligence, but a lot of it is just how do we move these numbers across a copper wire faster?
That is the engineering in AI engineering. It is easy to get lost in the philosophy of, is it conscious? But the people making it work are asking, how do I minimize the CPU to GPU kernel launch overhead? Speaking of which, Daniel mentioned CUDA graphs. That is a very technical point, but it matters. Usually, every time the Scout model makes a guess, the CPU has to tell the GPU, okay, do this math now. That telling takes time. CUDA graphs allow you to record the whole sequence of commands, so the GPU can just run the whole speculative loop without waiting for instructions from the CPU. It is like giving a chef a whole recipe at once instead of telling them one ingredient at a time.
It is all about removing the friction. Every millisecond counts when you are trying to hit that real-time feel. I'm curious about the zero quality loss claim again. Is there any edge case where the judge might be tricked by the scout? Like, could the scout's guesses subtly bias the judge's final decision?
In the standard implementation, no. The math is very clear. If you use rejection sampling, the final output is drawn from the exact same probability distribution as the target model. However, there are lossy versions of speculative decoding where you might accept a good enough guess to save even more time. But those are usually used for low-stakes things like internal search. For anything public-facing, people stick to the lossless version. It is one of the rare free lunches in technology.
I love a free lunch. Let's talk practical takeaways for a second. If someone is building an AI-powered tool right now, what is the entry-level move for speculative decoding?
The entry-level move is vanilla speculative decoding. Find a small distilled version of the model you are already using. If you are using Llama 70 billion, use Llama 1 billion as your drafter. Most inference servers like VLLM make this a single configuration line. You will likely see an immediate 2x speedup without changing a single line of your application logic.
And if they want to get fancy,
Then you look at Medusa or EAGL. Specifically, EAGL 2 is the one most people are migrating to if they have the ability to add a plugin to their model. It requires a bit more setup because you are adding a small head to your model, but the speedups move from twice as fast to 4 or 5 times as fast. It is worth the effort if you are running at scale.
and what about benchmarking? How do you actually measure if this is working? Is it just tokens per second?
Tokens per second is the headline number, but the real metric is inter-token latency. That is the time between each word appearing on the screen. Speculative decoding makes that number much lower on average, but it can make it jittery. You might get 5 words instantly, then a tiny pause, then 5 more. For most users, that feels faster than a steady but slow stream. You also want to track your acceptance rate. If your scout is only getting 10% of its guesses right, you need a better scout.
It is like watching a fast typist who occasionally has to hit backspace. It still feels faster than someone hunting and pecking at the keys perfectly.
And for the real power users, look into Mamba drafters if you are dealing with huge context windows. If you are asking an AI to summarize a whole book, a Transformer scout will eventually choke on the memory, but a Mamba scout will hum right along.
This whole discussion makes me realize how much invisible work goes into the AI we use every day. We see the clever answer, but we don't see the scout running ahead, the judge vetoing guesses, the tree attention masks, and the CUDA graphs all firing in milliseconds.
It is a symphony of micro-optimizations, and the coolest part is that it is all open source. The papers Daniel cited, Leviathan, Medusa, EAGL, these aren't secret corporate formulas. They are open research that anyone can implement. It is a very exciting time to be on the engineering side of this.
It feels like we are in the deployment era now. The models are huge and smart, but now we are obsessed with making them useful, cheap, and fast. Speculative decoding is the poster child for that shift.
It really is. We have moved from can it do it to can it do it for 1 million people simultaneously without costing a fortune, and the answer, thanks to these tricks, is a resounding yes.
Well, I think we have thoroughly unpacked why the scout and judge system is taking over the world. Where do you see this going next? Do you think we will eventually have hierarchies of speculation? Like a tiny model guessing for a medium model that guesses for a giant model?
Cascaded speculative decoding is already being researched. You have a 70 million parameter model drafting for a 7 billion, which drafts for a 70 billion. It is like a relay race. The efficiency gains start to diminish after a while, but for the truly massive trillion parameter models, a 3-tier system might actually be the only way to make them usable for chat.
A relay race of AI models. I love that image. It is just scouts all the way down.
That is the future corn, faster, smarter, and somehow using more models to do less work.
Well, that is a wrap on speculative decoding. I am definitely going to be looking at my chat windows differently now, imagining those little scouts running ahead of the text.
Once you see the jitter of a speculative sequence, you can never unsee it. It is the heartbeat of modern inference.
Thanks as always to our producer, Hilbert Flemingtop, for keeping the gears turning behind the scenes.
And a big thanks to Modal for providing the GPU credits that power this show. They are actually a great example of a platform where you can deploy these speculative stacks incredibly easily.
If you are enjoying the show, a quick review on your podcast app really helps us reach new listeners. It is the best way to support what we are doing here.
This has been My Weird Prompts. We will see you in the next one.
Stay curious, everyone. Bye.
Goodbye.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes